fluid times the mole fraction. And that's something that you can kind of intuit by looking at these images. The surface area available to the solvent decreases almost proportionally to the mole fraction, and so your pressure in the solution would be the pressure in the pure times the mole fraction. That's essentially Raoult's law. If that law holds, you'll have behavior that looks like this. Can you all see the line that connects the two dots that has PA plus PB over A is equal to PT across it? Okay, that line represents the total pressure in a solution of A molecules and B molecules according to what Raoult's law predicts. And you'll notice that this is the mole fraction of A. I should have drawn a little 1 here on the x-axis. As the mole fraction of component A goes to 1, when it's mole fraction 1, it's pure A, you'll get a pressure, a vapor pressure, that's equal to PA star. We said PA star was the pressure of pure component A. If the mole fraction of A is at 0, that means you've got pure B solution. And so the pressure that you would observe above a solution of pure B would be PB star, right? And all mole fractions in between, the sum is, or the total pressure is just the sum of PA plus PB, which would be the pure pressures times their mole fractions, and you get a linear relationship. The total pressure would move linearly from one pressure of the pure to the other pressure of the pure. The pressure of one component of pure component A and the pressure of pure component B. That's the behavior that you would expect if all of those interactions were equivalent. But because that's never the case, you never quite get Raoult's laws. You can never just assume that two species are going to have the exact same kinds of intermolecular forces. And so in reality, you get diagrams that look like that one on the left. That was given, that was figure 6.8 for carbon disulfide and propanone. And you can see that there's something certainly other than linear behavior for that line that connects the two pressures. And all of that's saying is that you get kind of interactions between those species in solution that cause them to have higher or lower vapor pressures than they would have if you were just multiplying their mole fraction times their pure component vapor pressures. Right? So no solutions are ideal. There are definitely changes in interactions between one pure substance and another. When you combine them together, you don't necessarily get the same interactions, and so you don't get that behavior predicted by Raoult's law.
So what uses it?
What's that?
What uses it?
Well, you see, I was hoping I could get to this. Your book covers this a little bit. I don't quite have lecture notes drawn up for it, but Raoult's law tends to hold at the limits, right? So as you're moving over to pure component A or pure component B, that linear relationship will tend to hold. With an exception, it'll hold for the species that's in excess. And so you have to kind of imagine, I'll draw it for you to make it easier to imagine. If you've got, I'm going to draw them as circles or squares and triangles. If you've got a solution that's made up of molecules that are all the same type, and that's the principal component. In general, any given one of these molecules will, on average, be surrounded by other molecules of its type, right? And so if this is component A, then a molecule chosen at random is going to be surrounded by other A molecules. And when we talk about vapor pressure, we're discussing the forces that tend to bind these A molecules into the liquid state. And so if A is in excess, it'll feel forces that are exactly equal to what it would feel if it was in a pure state, right? So even though you might have B molecules scattered at some low concentration throughout the solution, on average, your A molecules are surrounded by other A molecules, and so the vapor pressure and the forces that bind them to the solution are the same as they would feel in a pure substance. So at mole fraction of A goes to 1, so you're looking at a pure A component in the limit that you've got pure A, which is a highly dilute solution, you're going to have a pressure that is that's equal to PA star times the mole fraction, right? That holds for whichever component is in excess. So you go over to mole fraction of A is 1, then the A molecules are going to be exhibiting PA star vapor pressure. If you go to mole fraction of A equals 0, now you've got a bunch of triangles in the solution. And every once in a while there's a little square somewhere. Well, on average, those triangles are surrounded by other triangles, and so the forces that bind them into solution are going to be the same kinds of forces that they feel in a pure substance. And so as you go over to mole fraction of A equals 0, and therefore mole fraction of B equals 1, you'll be exhibiting a vapor pressure that is comparable to the vapor pressure of pure B, pure component B, right? So Raoult's law holds for those components in the limits that they are the principal component in the solution. That brings up another subject, and that subject is how do we derive expressions for the chemical potentials of the minority component of the solution. And so Raoult's law, if you look at this species, you can tell that the forces that it feels when it's the minority component in the solution are very dissimilar to the forces that it would feel when it's the majority component. When it's the majority component, it's surrounded by other molecules of the same type. When it's the minority component, it's surrounded by molecules of an entirely different type. And so the forces binding in the solution will be different in magnitude than the forces binding in the solution when it's the majority component. Forces binding in the solution when it's a minority component are different than the forces binding in the solution when it's the majority component, and so we end up needing to have a new expression for the pressure of that component. And again, pressure ends up being used to communicate the chemical potential. And this is not in the notes, but it's in your book. This is where Henry's law comes from. For Henry's law, so I'll put the two laws together. For Raoult's law, we said that the pressure is equal to P star times the mole fraction. For Henry's law, we're going to say that the pressure is equal to something called the Henry's law constant times the mole fraction. And the Henry's law constant ends up being just whatever, it'll have units of pressure, same as this had units of pressure. But it just ends up being whatever magnitude you need it to be in order to fit the experimental data for the pressure of that minority component in solution. So Raoult's law allows us to derive this expression for the Gibbs free energy. You say that chemical potential in a liquid is equal to the standard chemical potential plus RT times the natural log of the pressure observed. The pressure is pressure of the pure times the mole fraction. And so you end up with chemical potential of the liquid is standard chemical potential plus RT times the natural log of the pressure of the pure plus RT times the natural log of the mole fraction of the component in the solution. These two terms, mu naught and RT line P of pure, can be combined into one mu expression we'll call mu star. And so we get the expression that the chemical potential of the liquid is standard chemical potential mu star, but this again is not the chemical potential of 1 atmosphere. This is the chemical potential of 1 atmosphere. This is the chemical potential of this is the chemical potential of the vapor pressure. So we had to correct the standard chemical potential for the vapor pressure of pure. We combine those two together into one, chemical potential term, and we get that the chemical potential is this mu star times natural log, RT natural log of the mole fraction. That is the expression for Gibbs free energy of species that obeys Raoult's law. Notice that, again, because the mole fraction is something that's less than 1, the natural log of the mole fraction will be something with a negative sign on it. And so what we're saying is that the chemical potential of the species decreases when it goes in solution, right? Same way we showed that the chemical potentials of those gas species decreased when they mixed. The chemical potentials of these liquid species also decreases when they mix to form solutions. An analogous term that I didn't put in my notes, but an analogous term can also be derived using Henry's law. Just imagine that instead of writing P pure times XA here, we write Henry's law constant times XA, and we execute the same steps. We'll end up with an expression for the chemical potential of the solute that says that mu of the solute is equal to mu star the solute plus RT times the natural log of the mole fraction XA, where mu star is mu naught plus RT times the natural log of the Henry's law constant. And now we get to the fun part. To play with graphs again. So we're just taking a look at those pressure, or the Gibbs free energy versus temperature curves. We had Gibbs free energy versus pressure. We've got Gibbs free energy versus temperature. These are the same kinds of curves that we were looking at last time, except now we're just going to consider 2 points of intersection at a time. So to address the melting point changes, the changes in melting point that happen when you dissolve a solid or a solute in a solvent, we're just going to use the solid and the liquid curves, right? So if you remember, the solid curve had a smaller slope than the liquid curve did, and they intersected at some point, some equilibrium point. We knew that that point was being the point of equilibrium between solid and liquid. That was the melting point temperature. And so here's your initial melting point temperature. Well, we just said that the Gibbs energy of a solution is always shifted to lower energy relative to the pure liquid, right? And so we could, if we wanted to plot the Gibbs free energy of the solution curve, we'd simply shift that Gibbs free energy of the liquid down a little bit to account for the decrease in G. you'll notice that what that does is that shifts the point of intersection between the solid and the liquid curves backwards to lower temperatures, right? Shifts it backwards to lower temperatures. This means that the melting point has lowered. This means that in order to get this this thing to melt, we're going to have to bring it down to even lower temperatures than we would for the pure. One of the ways that that was explained to me when I was first studying this stuff was the reasoning that when something freezes, it disincludes solutes. So if you want to take some ice and you want to freeze, or some water, salt water, and you want to freeze it, before it can become pure water, it has to somehow compartmentalize all of those ions and get them out of the crystal structure, because there's no room for ions in the crystal structure of water, right? And so there's some energy that has to be invested into separating the solid, the pure water from the ions in solution. That energy wasn't required when you were just trying to freeze pure liquid. But now that you've got this thing in solution and you want to freeze it, you're going to have to pay kind of an extra energetic debt to be able to keep all of those ions excluded from the crystal of the solid. So that's how you can kind of think of the necessity to lower that temperature, right? There's just a little bit higher expenditure that you have to pay to get that to happen. So we can look now at the we can address the boiling point shifts. You take the pure liquid curve and the gas curve. Remember, the gas curve had a much larger slope than the liquid curve. They've got some point of intersection. You notice that the solution is shifted down relative to the liquid because Gibbs free energy of the solution is always lower. And so that curve shifts, and when it does so, the point of intersection between the gas and solution curves shifts to the right relative to the point of intersection between the gas and pure liquid curves. So the point of equilibrium between the solution and the gas shifts to higher temperatures. Your boiling point has been elevated, right? The way you can think of this is in the solution, you've got a lower free energy than in the liquid phase, right? So you're at a lower chemical potential, you're at a lower, I guess you're at a more stable state when you're in solution than you were in the gas. And if we think of the relative stabilities of the gas and the liquid phases as they pertain to boiling, the more stable you are in the liquid phase, the less eager you're going to be to go out into the gas phase, right? If the relative stability of the liquid phase is quite low, then you're at a low potential and you're happy. And so essentially, the solution molecules, the solvent molecules in solution, are happier to stay in the liquid phase when they're in solution than when they are in the pure liquid. Therefore, it's easier to kind of coax them out of the pure liquid to go into the gas phase than it is to coax them out of the solution and drive them into the gas phase. Does that make sense? Go ahead.
So one question. Anyway, so why is it that when you put salt in water, it boils faster then? You have water, you have salt, it boils
It
faster.
doesn't boil faster. It boils at a higher temperature. And that's exactly because of this. Your T shifts. When you got pure liquid, you're boiling at some temperature. You put the salt in solution, it shifts the boiling point to a higher temperature. And so now you boil at a higher temperature and you cook faster. You cook faster.
It's going to be at 100 Celsius.
It'll be at something above 100 Celsius, right? So you put salt in the water, now you're going to boil at a higher temperature, and that means your stuff is going to cook faster because you'll be able to achieve higher temperatures inside your pot, right? So it's not actually that it boils faster, it's that it boils hot.
salt and water, you can cool. Some lower.
Yeah? Okay, so I feel like you guys got the solid liquid equilibrium, but how about the gas liquid equilibrium? Does that make sense? Because the solution phase is at lower chemical potential, the molecules in the solution, the solid molecules in the solution are relatively happy to stay there, and so if you want to drive them out, you're gonna have to stick a bigger fire under them to drive them out into the gas phase, relative to the temperature that you would have had to put them in the pure liquid, drive them in the gas phase.
Is that because of the ionic interaction? I mean, let's say water and salt.
Right now, we're mostly just dealing with ideal solutions. Ionic solutions are not ideal. All of that stuff does matter, and we'll try to talk about that more. We're going to get into chapter 9, the thermodynamics of ionic solutions, and we'll start to learn about what the different things are that you have to pay attention to for ions. But this is all just conclusions that you draw from assuming that you've got ideal solutions, in which the interactions between solvent and solute are identical.
Well, what would be an example of an ideal solution?
They used hexane and toluene or something like that. Like two species that have comparable interactions. Hexane and toluene, both like non-polar molecules, roughly the same size, and so they're going to have dispersion forces that are equal in magnitudes, and they're identical in kind. So they're both dispersion forces. The dispersion forces hold hexane together, they hold toluene together. You stick hexane and toluene together in a solution, and now the solution is governed by dispersion forces of comparable magnitudes to the dispersion forces in the pure substances. But either way, everything else aside, you dissolve something into solution, you lower the free energy of the solution relative to what the free energy was of the pure liquid, and that gives rise to your changes in your melting point and your changes in your boiling point, just as we kind of shown there. Right? So, the second thing we want to talk about is the osmotic pressure. And the osmotic pressure, you can do the math, or you can just kind of like look at a picture. And sometimes I like the pictures better than I like the math. So I'll show you the picture first, and then we'll do the math. So, consider two surfaces again. Pure substance. And something that is not pure. So again, we're gonna relate this to solvent and solution separated by two compartments. You imagine that there's an interface here between the two solutions, or between the two liquid phases, and that interface is composed of a semi-permeable membrane that allows solvent molecules to pass from one side to the other, but doesn't allow solute molecules to pass from one side to the other. And you can kind of think of this interface as being a membrane with pores, and then you can sandwich these two faces together. And the two faces, the face of the solution and the face of the pure solvent, come together, they meet at this membrane, and now solvent molecules are allowed to pass through these pores from one side to the other. Yeah? At equilibrium, when you've got a condition of equilibrium between the two phases, the rate at which solvent molecules from this side pass over to this side is equal to the rate at which solvent molecules from this side pass over to this side, right? But these solvent molecules over here have an advantage, and that is that they occupy the entirety of the surface area adjacent, that butts up against this membrane. Solvent molecules over here don't have it so well, because they're bumping shoulders with all these solute molecules, and so they occupy a lower surface area overall. Well, the rate of passing from one side to the other is going to be proportional to the surface area. So these guys have a hard time getting over, these guys have an easy time getting over. If we're going to achieve equilibrium between the two phases, we're going to have to give these guys an extra push, right? And that's essentially what the osmotic pressure does. When you take two situations like this, a pure liquid and a solution, and you bind them with a semi-permeable membrane, or you connect them via a semi-permeable membrane, there'll be an increased pressure in the compartment that has the solution. And that increased pressure is whatever pressure is requisite to give those guys the extra shove so that they can start crossing that boundary at the same rate that the other guys are crossing the boundary. Remember, equilibrium is all about equal rates. And so if rates of travel across that membrane are going to be equal, then the solvent molecules on the right-hand side that are in solution, they're going to have a little bit extra, a little bit stronger shove to get them to pass at the correct rates. All right. So we can look at that image and we can do some math. If we do the math, we can cast this problem in terms of the chemical potentials. You have, at equilibrium, the chemical potential of the pure liquid is equal to the chemical potential of the solution. The chemical potential of the pure liquid is just a function of the pressure, right? Whatever the vapor pressure is that the pure liquid usually exerts. The chemical potential of the stuff in solution is going to be a function of the mole fraction. We know the chemical potential is lower when the mole fraction lowers, right? Or when they go into solution, the chemical potential is lower. And it's also going to be a function of that increased pressure. So this guy was at pressure P, this guy is at pressure P plus pi. You can break this chemical potential as a function of the mole fraction and the increased pressure. You can break it apart into two terms. One term will be the RT natural log of the mole fraction that we got, where that's the negative contribution to the chemical potential. And the other one is the chemical potential of P plus pi. We know from that dG is VdP minus SdT term that we have for differential changes in G, that the pressure dependence of changes in Gibbs energy goes as the volume. And so we can write that this term, chemical potential of P plus pi, is equal to the chemical potential of P plus the VdP term, right? Our dP is just pi, the osmotic pressure, it's just the change in the pressure. And so we can put all of those terms together. Remember, you got equilibrium, so left-hand side is equal to right-hand side. Left-hand side is just the chemical potential of the pressure P. The right-hand side is going to be chemical potential of pressure P plus V times pi plus RT times the natural log of the mole fraction. These two terms cancel, and you get this term, the negative RT natural log of the mole fraction, is equal to pi times VA, and with several manipulation steps, this becomes what is equation 6.21 in your book. Go ahead and read the derivation in your book so that you understand how you get to casting the osmotic pressure in terms of the number of B molecules. I might end up going over that a little bit on Tuesday with you. But essentially, what we've done here is we've shown that